Welcome to lesson 31 of this Arduino C++ course, and today once again we're going to be looking at stepper motors, particularly the 4-wire bipolar stepper motors, often sold as sort of NEMA motors. And in part 2 we're going to be looking at indexing stepper motors. So going over to the breadboard, you can see that I have my stepper motor running. This time I've got a NEMA 17. And it's doing the code from version 5 of lesson 30. So it's rotating 360 degrees, stopping for 1 second, rotating in the opposite direction, and again stopping for 1 second. The difference is that this is using non-blocking code, so other things can happen at the same time. Now, obviously, the stepper motor is moving to the correct position every time, but if I just stop the stepper motor, change its position and restart, now you can see that it is not starting and stopping in the same position. Let's change it again, turn it on, and we can see it's stopping and starting in a different position again. And the problem with stepper motors is, although they're very accurate, when they start up, they have no idea what position they are in. It's not like a servo. They basically wake up and they move a number of steps from their current position, but have no idea sort of what angle they are pointing to when they start up. So indexing is a way of letting the stepper motor know where, if you like, the start position is. It's finding a 0 position for the stepper motor to move from. So let's have a look at one of the types of zeroing of a stepper motor. So here we have my 3D printer, and this 3D printer has 4 stepper motors. Now there is a stepper motor here that's responsible for moving the printer head across the bed. There's another stepper motor underneath that drives the bed backwards and forwards. There's a stepper motor sort of out of sight down here that does the Z-axis, the up and down. And then there is a stepper motor in the printer head that moves the filament through. Now, when it comes to the filament, we're not really worried about indexing the stepper motor, because all we need to do is say we want to move the filament a certain distance, which equates to a certain number of steps. So we don't need to worry about indexing the, if you like, the filament. However, when it comes to the head here and its sort of X and Y axis, we need to find out exactly where 0 is. So if you watch this limit switch, as I start the video, we can see the head moves across and it makes contact with this thing here, moves back and then touches it again. Now it does that, and then the bed moves behind it and zeroes the Y axis. But the important thing here to see is that as it's come across, as soon as it's hit this limit switch, it now, if you like, has a 0 position, so it now knows how many steps to move across the bed to get to any point on the bed. So for today's lesson, I'm going to call that linear zeroing, because the unit that is moving, if you like, in a 2 directions, left or right, whereas we're also going to look on the workbench at how we deal with rotational zeroing. So something that is spinning round and round in circles, something like maybe a model railway turntable, where it's not just going to come to an end stop, it's got to continue to rotate and rotate in both directions. So we're going to look at how we would do the indexing for both of those scenarios. So the first thing we're going to do is go over to the Digital Town website. Link, as always, is below the video so that we can take a look at today's circuit diagram. Once you're over on the Digital Town site, as always, just scroll down. We're on lesson 31, so we're quite a long way down. and there you will find the circuit diagram for today's lesson. Just click on that and you will get a slightly larger version that you can expand up. So let's have a quick whiz through the circuit and I'll show you what's going on. So in lesson 30, we set up the stepper motor. We had our 12-volt supply, power supply, that is for the stepper motor. We've then got this link coming over here, the 5 volts that is powering the circuitry of the A4988 driver. There was this capacitor here that was just there to smooth the current if that is required. So that's the last lesson circuit. What I've done for this lesson is I've added a few extra components. Very simple. We've got an LED with a 330 ohm resistor. Here I have got a Hall sensor. Now the Hall sensor is triggered via a magnet. So as it senses the magnetic field, when the magnetic field gets above a certain value, then this sensor will be triggered. Here we have a limit switch. Now I'm using the same type of limit switch as you saw on my 3D printer. And when it comes to limit switches, when you're looking to use a limit switch as your zeroing option for your stepper motor, make sure it's a pretty decent one. You do not want a sort of a wobbly loose connection. The type of button that I've got here that I'm just going to be using as a push button, if you try to use that as a limit switch, I think you're going to have quite a few problems because these are in a way a little bit more unstable, and when you press it, I'm not quite sure that it would be as accurate as this sort of limit switch. So you want to make sure that you've got a fairly decent limit switch. Now, this limit switch could have been a photo interrupter. There are other types of limit switch you can use, and you need to think a little bit about the environment that you are working in. So for instance, the limit switch on my 3D printer is one of these. As you can see, there's quite a lot of dust around the 3D printer, but it's not so bad that it is, if you like, clogging up the switch. The same if I used a photo interrupter. If there was a lot of dust around, that could get dirt on the sensor. Whereas a Hall sensor, being magnetic triggered, is not going to suffer from dust in the environment. However, obviously if there's other magnets in the area, this is going to be totally useless. So choosing your limit switch is important, and if you like the device you're going to use, you just need to think about the circumstances that you are going to run the project under. Now for today's code, for the linear example, I'm going to be using the mechanical limit switch. For the rotational indexing, we're going to be using the Hall sensor. Now the reason for that is if you have got linear movement, you can move over and press on the switch. If you've got something rotational, that's going to be a little bit difficult to keep pressing on the switch. There is a way that you can make it happen, but I wouldn't advise it. So for that we need a different type of limit switch, and for that I'm going to use the Hall sensor. So moving over to the IDE, we're going to get on with the first sketch, which is Stepper Index version 1, and as always this is the test sketch, and this is going to check that our connections to the stepper motor, the switch, the LED and the Hall sensor are all working correctly, because there's nothing worse than having a problem in your project and finding out after you've sort of worked through miles and miles of code, you suddenly realize you haven't connected the button correctly, or your ground's fallen out, something like that. So this sketch, literally all it's going to do is it's going to spin the stepper motor. It's actually using the code from stepper version 2, I think it is, off the last lesson. So it's just going to be working through the steps, and then what I'm going to be able to do is I'm going to be able to trigger the Hall sensor. So as the unit rotates, there's a little magnet on the end of that black arm, and as it spins round, it will trigger the Hall sensor if that's working, and we will see an LED light up or go off. Then what I can do is uncomment this bit of code. That's going to check the switch, and then I have my limit switch code. So let's get this one uploaded. So the stepper motor is rotating away, and you can see that as it passes this hall sensor here, you can see there is an LED flashing on the breadboard. There's also an LED that triggers on the hall sensor. So at that point, I can see that I am getting a signal now coming from my hall sensor through my UNO and to my LED. Now all I'm going to do is I'm going to quickly comment that out, uncomment this, and quickly upload the code. Now what should happen is as I press this button, the LED should go on and off. And this is a good way of testing actually that we are using non-blocking code, because if I'd been using micro delay on the stepper motor, this button wouldn't work in the way that it does. So we can see that that one's now connected correctly. So now it's quickly back to the IDE, comment out that one, uncomment the next one, and get it uploaded. Now it's just a case of pressing the limit switch, and I can see now that I'm getting a connection from my limit switch to my UNO and back to that LED. So at this point, I now know that all the components in the circuit are working correctly, and we can start getting on with our first proper sketch. And that's going to be indexing in the linear method. So that would be the type of indexing that we saw on the 3D printer, where the unit would move in one direction until it reaches the limit switch, and then it's zeroed itself once it's touched that limit switch. Now, just before we do the programmable side of the limit switch and the indexing of the stepper motor, there's also some, if you like, physical things that you need to think about. So this is a NEMA 17 stepper motor with a gearbox, and this has a very high torque unit. Now, the problem with a gearbox is this is a pretty good quality one, but there is a tiny amount of backlash in the gearbox, and it really is a tiny amount. It's probably less than half a degree. It's a pretty well made unit. However, the problem with that is that it means as the stepper motor changes direction, that half a degree is going to be added in to the movement. So if you went clockwise, what you thought was going to be 360 degrees and then came back 360 degrees, you won't actually finish up in quite the same position, because you will be out by the amount of backlash in the gearbox. So if you're using something with a gearbox, really it's only useful for turning in one direction, or where you don't need sort of super accuracy. This is also important to think about when you're building a project. So on my 3D printer, the belts make the 3D printer pretty accurate. You can use lead screws. Those are also accurate, providing you have anti-backlash nuts. But if you were to add a worm wheel and gear system on a stepper motor, then the backlash in those gears is really going to upset your indexing. So indexing isn't just about getting the code right, it's also about getting the mechanical side of your project correct. So the goal of sketch 2 is we are going to press the one button on the breadboard. When that button is pressed, then the stepper motor will start to turn in an anti-clockwise direction until the limit switch is triggered. At that point, it's going to assume that it is indexed and stop. So looking at the sketch, obviously I've still got all the buttons set up as before. I've got an indexed value. Now that's going to be set as 0 to start with, so it is not indexed. And we're also going to have a value here, move stepper equals 0. Now this is going to tell the system when to move the stepper and when not to move the stepper. Now one of the things, just coming back to the breadboard, just to show you what I mean by that, when my 3D printer starts up, it does not instantly index. It waits until I basically press something on the computer to say start printing. Then the first thing it says to me is there anything on the print bed? Do you need to remove something? Only when I click OK, which in my case is going to be the index button, does the stepper motor then start to move the bed. Now this is quite important in your projects. I once built a model railway turntable that indexed at startup. I thought that was going to be a great idea. As soon as I turned the layout on, the turntable rotated and indexed itself. That was great until I left a train halfway across the turntable. When I turned the layout on, instantly threw my train basically off the layout. So that is why very often it is best not to index the stepper motor when you turn the system on, but rather wait for it to be triggered. So for our example on the breadboard, this is going to be my start button. This is going to be my limit switch. So when I press this switch, then the stepper motor is going to assume that it has become indexed. So working my way down through the sketch, all of the setup is the same as in the previous sketch. Now we come to the stepper motor code. Now before we had the if statement, and it was basically if it's time to take a step, we're going to take a step, and that is dealt with in this little bit of code here. Now we're not even going to start checking the time for the next step unless the value of move stepper is greater than 0. And that's going to get triggered when I press that button. Now, one of the other things here, that when we are looking at the movement of this, if the stepper motor is not indexed, it's going to continually read the value of the limit switch. So this the stepper motor is a 200 step stepper motor, but because we go round the loop twice for each step, one to set the step pin high, one to step it low, we've got the equivalent of 400 steps per revolution. But every time it takes one of those sort of half steps, it's going to check to see what the value of the limit switch is. Now that mechanical limit switch, because it's on a pull down resistor, when it is greater than 0, when it goes 1, when it goes high, then it means that the switch has been pressed. At that point, it's going to set the value of move stepper to 0. That means that the stepper motor, because that's now a 0, the stepper motor will stop moving. I'm going to set my value of index to 1, and I'm going to set my value of step counter to 0, because at this point we are indexed, and obviously then we are going to serial print the value indexed. Now that is if the move stepper value is greater than 0. If it's smaller than 0, then that brings us down to this else statement, and in the else statement all I'm going to do is read my switch. So at this point I don't want to be allowing myself to press that switch while the stepper is moving. If I press that button and the index value, if basically I haven't indexed the unit yet, then it's going to set the step direction to anti-clockwise. So we're going to digital write the direction pin to that step direction. Now the stepper motor is going to move anti-clockwise, and I'm going to set the value of move stepper to 1. So at that point, this will start to run, the stepper will start to rotate, and it will keep going until I press the limit switch. At that point, everything's going to stop. So let's get that code uploaded and see it in action. So here we go. I'm going to press my start button. The stepper motor now rotates anti-clockwise until I press the limit switch, at which point the stepper motor stops, and as far as it's concerned, that is now its indexing point. So now we've seen how to index the printer from a sort of a linear perspective. What we're going to do now is move the stepper motor to various positions once it's been indexed. Now, rather than me adding lots of buttons, all I've done is I have created an array with 5 different positions. So when I press my button the first time, it will index the unit. Press it again, it's going to move it to a position of 2000. Then it'll move back to position of 500, forward again to 3000, back to 35, forward again to 1500. Now this byte here is just going to keep track of where I am moving through the array. And then we've got another value here. This is the stepper target, and this will contain one of these values and is the target that the stepper motor is aiming to get to. Now moving down the sketch, we're going to come down to line 36, and you'll see here I've given the step counter a value of -1. Now the reason for that is within the system, when the system gets indexed, it has a value of 0, but this is required to index the system, as you will see in a bit. Then coming down a little bit more to line 66, we're now going to start to look at how the whole system works. So that stepper target, it will keep moving the stepper motor if the stepper target is not equal to the step counter. Now, if you remember, all my targets are greater than 0. So if I'm aiming for a minus figure, that is why this value here needed to be set to -1. So scrolling down again to the main loop, let's have a look at some of the changes that have been made to the code. So the first thing is, depending on the direction of travel, we are either going to decrease the value of the step counter or increase the value of the step counter. Because obviously we're starting from 0. If we're moving away from the 0 point, then we're going to increase. Moving back to that 0 point, we're going to decrease the value. Coming down, then what else have we got? Our next section with the big change, obviously when the stepper motor, we have this thing here, is the stepper target not equal to the current step counter. If it's not equal, it's going to keep moving, but if it does become equal, then we're going to set the move stepper value to 0, and I'm going to serial print out the fact that it has now arrived at the correct position. Now, coming down a little bit further, the other change that has been made, before we had an if statement to do with the indexing. Now we're going to do something else with the switch. So if the switch is pressed, if it's not indexed, it will do just as it did before. It's going to wait for the stepper motor to index itself. If it has already been indexed, then what it's going to do is it's going to set its next movement target, the next value in my array. Now this bit normally would be, if I was doing a project, maybe you want to move the stepper motor to different positions using a set of buttons. this is where you would set, if you like, your trigger for those buttons. If I press this button, I want the stepper target to be whatever number I want it to be. So what we're going to do here, it's going to work through the array. Obviously, if it gets to a value greater than 4, it's got to go back to 0 because I've only got 5 elements in my array. Each time I press the button, it's going to give a T for the stepper target, and then the count is going to give the current step value. Next, we have to work out which direction to move the stepper motor in. So if the stepper target is greater or equal than the stepper counter, then we're going to move the stepper motor in a clockwise direction. Otherwise, we're going anti-clockwise. Then all I'm going to do is set that direction. And finally, I'm going to turn the system on so that at this point, moving back up here, because this is now greater than 0, the whole stepper motor system is going to start moving. So now let's watch the system in action. I press the button. Stepper moves anti-clockwise until I press the limit switch. It's now indexed. Now what happens is if I press the button again, if you look in the serial monitor, you see that it now has a target. It's going for a value of 2000, and it started from a value of 0 because it had just been indexed. I press the button again. Now it's moving anti-clockwise because it's trying to get back to a target of 500, and it started from a value of 2000. Press again. Now we're going clockwise because we're aiming for 3000 and trying to get there from 500. And if I keep pressing, I start to work through the rest of the values in the array. Finally, I get to the last value, and this time if I press it again, it goes to the first value, and we just start the whole system again. But at that point, you can see that we now have a stepper motor that every time it starts up will move to the same position, and we can prove that just by turning off the Arduino, moving the system, turning it back on. There we are, we're indexed, and we can start moving from that indexed position again. So now we've designed a system that does exactly what we see here. We've got the stepper motor moving across, indexing itself. You can just see the bed in the background moving, and then the head is going to move to a position that, if you like, is the position that we have set in our array. So now we've sorted out, if you like, linear movement, we're going to look at rotational indexing. Now, for those who build model railways, this is particularly important if you want to build a turntable system. Now, for this, there is a tiny magnet on the end of this arm, and that's going to trigger the hall sensor here. The first thing I want you to notice is as the arm comes round, you'll see the LED come on just here as the hall sensor senses that magnet. But notice there is quite a range of movement here that the arm can move within, and the hall sensor is triggered. So one of the issues that you have when using something like a hall sensor is what we're actually trying to capture is the moment that the hall sensor is triggered. So just about there. Obviously it'll be more accurate from the code, but the other thing to be aware of is the stepper motor has to be turning in the same direction every time it indexes, because if I indexed from the other direction, I'd probably be about 4 degrees out. So it's very important that we always index while rotating in the same direction. So in this example, I'm going to be indexing in a clockwise direction. So for this first sketch, all we're going to do is make sure that we are getting a consistent number of steps per rotation. Now you might think, well, surely a stepper motor always takes the same number of steps per rotation. That's true, but there are some things when you're doing rotational indexing that can cause some issues. Now going back to the webcam, one of the things that can cause you some issues is your actual project design. Now, what is often missed with stepper motors is when it's spinning, it looks like it's spinning smoothly. Actually, it's not. It's taking one step after another. Now, when those steps are fast enough, it all looks very smooth. But what can happen if you're not careful with your project? Imagine this arm here was a little bit more flexible. At certain frequencies, you can hit a resonant frequency where this actually starts to oscillate in a way that it exaggerates the stepper motor's movement. Now, if I was building, say, a model railway turntable, because of the friction of the turntable, that would be removed. But for a lightweight project like this, it's something to be aware of, that there can be vibrations that get exaggerated over the length of this arm. And that could actually cause this arm to flick forward and trigger the stepper motor, if you like, the sensor, and then flick back. So it would trigger this too quickly. So the first test we're going to do is just make sure that we're getting the correct number of steps per rotation. So coming back to sketch 4, we've got a step counter and obviously our direction that we're moving in. Coming down to the main loop, we have our basic code that is just moving the stepper motor, in this case in a clockwise direction, and every step it takes we're going to increase the value of step counter. Now coming down here, there's a little bit of some weird code. I'm going to read the value of the Hall sensor, and if it's smaller than 1, that means that the Hall sensor has been triggered. So by default, the Hall sensor is high. As soon as it senses that magnet, it goes low. But you'll notice I've got a little bit of strange code in here, and I'm only going to deal with this value if the step counter value is greater than 50. Now, the reason for this, if we go back to the workbench, if you remember when I moved the stepper motor, let's just do the power and turn this on. As the stepper motor comes round, it triggers the Hall sensor. Now I want you to imagine for a moment that the stepper motor has stopped in that position. Now when I restart the stepper motor, it will instantly think it is indexed, but actually the index position we want is just as it went high. That is actually probably going to be 3, 4, 5 steps later. So that bit of code says unless the stepper motor has done 50 steps, any Hall sensor reading doesn't count. That means that if it started here, it would do a full rotation and come all the way round before it felt that it was indexed correctly. So coming back to the code, providing it's done over 50 steps, it will now serial print out the value of step counter, reset the value of step counter to 0, and just as a little extra, when the Hall sensor is triggered, it's going to go, the LED is going to go high, and when it's not being triggered, it's going to go low. So let's get that code running. So the code is up and running. As you can see, let's move that over a little bit more. You can see that as it goes past the Hall sensor, you can just see the LED over in this corner just flashing. The LED on the Hall sensor is quite hard to see as it goes by. But the other important thing is looking at our serial monitor, we can see that we're getting a constant 400 steps. Now, if I go back to the breadboard and change this little connector here, let's just push that up, turn the system back on. Now it's doing half steps, and as you can see, we're now starting to get a constant value of 800 because it's double the number of steps. So at this point we can see that we are getting the exact number of steps that we expect. We're not getting any sort of flexibility in our measuring system. And of course that's important, because if you're not getting a constant value down here, then anything you build from that index point is always going to be subject to an error. So sketch 5, very similar to sketch 3, where we did the linear indexing. Once again, we've got a value for indexed, we've got a move the stepper, but obviously we've also got that step counter. Coming down to the main loop, as in the last sketch, we've got that step counter that is incrementing. We're checking the value of the Hall sensor, except this time when we get the value, when the Hall sensor gets triggered, this time, providing it's done more than 50 steps, we're going to set the index value to 1. I'm going to set the value of move stepper to 0, so that's going to stop any stepper motor movement, and I'm then going to set the step counter to 0 because we're indexed, and all of that is going to be triggered in exactly the same way with that one button on the breadboard. So the code is uploaded, and the goal now is that the stepper motor indexes itself in exactly the same position each time. So if I just reset the board, press go, you can see that that rotates back to exactly the same position. So at that point we can see that our indexing system is working. So for this final sketch, sketch 6, I'm going to start as with the previous indexing system, where I press the button to index the turntable, then it's going to press the button again to move through these different steps in the array. Now, because this has got to stay within one rotation, I'm back to using 400 steps. So all of these values must be between 0 and 399, because there's only 400 steps in the rotation. And the reason that I've put them in this order is to make sure that we go clockwise and anti-clockwise, rotating between the two positions to get to the new position as quickly as possible. So let's have a look at this in action, and then we'll go through the code. So I've scrolled the code down here so that you can see the values in the array, and we'll see the positions we're moving to in the serial monitor. So the first press should index the unit. There we go, we are indexed. You can see that value has come up. Press the button again very quickly because there's no debounce on this. Oops, press that twice. You can see that what it actually did there was it moved to a position of 350, and because I didn't get my finger off the button quick enough, it instantly then jumped to a position of 200. So if I press the button again, you can see now that it's gone to that position of 100. Back to, what is that, 280. Now it should go anti-clockwise to 85. And now it will jump all the way round to 350. Now you'll notice again it goes anti-clockwise because it's quicker in an anti-clockwise than a clockwise direction. So this isn't just picking up any random direction, it's working out which is the fastest way between any two positions. So scrolling down through the code, the array system is exactly the same as in the linear system. The main changes round here, I've got this new variable steps per rotation, which for me is 400. It's a 200 stepper motor, but I can divide that by 2 because one, I'm doing half steps high and then the low, so I get the 400 steps. We're going to need that in our code. then coming down to the main loop. This obviously is where things get a little bit interesting. So as before, we've got our variable move stepper, which tells the system whether the stepper motor should be moving or not. And as before, we're going to be aiming for a target. Now, if we hit that target, then we are setting move stepper to 0 and the stepper motor will stop moving. As we go through this, one of the differences here is obviously we've got the step counter that decreases going anti-clockwise, it increases going clockwise, but because we're using a, if you like, a rotation stepper system, if the value of the step counter goes below 0, then we need to set the value to 399 because it's gone round a full rotation, and in the opposite direction, if the value goes over 399, we need to set the step counter back to 0 because we've got 400 steps per rotation, and we don't want to be getting into minus values. Again, we've got that bit where we are looking for the indexing at the beginning, and that code is still in there to make sure that it's done over 50 steps before it declares something that is indexed. Coming down to our button code, we've got our initial code for if the stepper has not been indexed. That's just going to set the stepper in a clockwise direction, and it's going to do that until it indexes itself. The opposite is once again where we're going to get a stepper target from those arrays. Now you would probably use your buttons or something else to set your targets in here. If it was a model railway turntable and you were doing DCC, you might be using the NMRA library to trigger the number of steps that you want it to move to. As before, we're serial printing out the target and the current position. But the difference now is that because we're doing a rotational system rather than a linear system, we now need to find out which is the quickest direction to get to the position that we want to get to. So the first thing we do is we have an integer here that is called find direction, and that we take the value, the stepper target, and we subtract that from that the current step value. Now, if the result of that is smaller than 0, then we need to add the number of steps per rotation to our value, and that will give us the correct value for find direction. All we then need to do is say if find direction is greater than the steps per rotation divided by 2, then you know whether you then know to turn anti-clockwise, otherwise you're going to turn clockwise. We then set the direction and start the stepper motor moving. It's as simple as that. So once that's done, I can just press my index. Once I've done that, we can start moving through the other positions. Usually the first one I'm not quick enough for. Oh, got it this time. Second position, third, fourth, fifth, back to the first. So I now have a fully indexing turntable system. So from today's video, you've got the code now to do either a linear or a rotational indexing system for your stepper motor. In part 3, I'm going to show you how to run multiple stepper motors at the same time. So that will be stepper motors moving in different directions at different speeds triggered by different things. That'll be an interesting little video to do. So I hope that's been useful for you. Any questions, please stick them in the comments below or email me on the Digital Town website and I'll get back to you as quickly as possible. And if there's other bits to be added, I can put them in the next video. Thanks for watching, and I'll see you in the next video. Bye for now.